presentation about co-propagation of distributed acoustic sensing in the L-band and 100 GB per second WDM coherent communication system. My presentation has 4 parts. First is introduction and principle. Nowadays, distributed fiber sensing based on telecommunication networks has attracted significant attentions, which can make the existing telecom fiber infrastructures into a large sensing network. Distributed vibration sensing system has particularly wide applications, such as fiber damage protection, earthquake sensing, and traffic detection. One of the most promising approach for distributed vibration sensing is distributed acoustic sensing, which has positioning accuracy of several meters and sensing distance up to 1,000 kilometers. DAS is different from traditional OTDR. DAS is based on coherent interference of Rayleigh backscattering light. DAS can be incorporated with coherent communication system through WDM, but the DAS system will occupy a sensing channel wavelength in the C-band, which is very unacceptable for the deployment in the existing optical network. Another problem of co-propagation is the co-propagation penalty. There are 2 ways of coexistence: co-propagating and counter-propagating. In the co-propagating configuration, sensing pulse and the data traffic propagate in the same direction, but the data bits will be seriously affected by nonlinear effects in the overlap area. In counter-propagating configuration, the sensing pulse and the data traffic propagate in opposite direction. All the data bits will be affected, but at a much smaller ratio due to the limited interaction time. So co-propagation has a much greater penalty and is more likely to cause outage. In this work, we focus on the penalty study of co-propagation configuration. Co-propagation penalty has been studied in previous work. It can be studied that both pulse peak power and pulse width has influence on the co-propagation penalty. Co-propagation is not allowed when pulse peak power reach certain power, so it can be inferred that reducing pulse peak power can reduce the co-propagation penalty. However, the pulse width must be increased accordingly when reducing the pulse peak power. Otherwise, the pulse energy will be reduced significantly, and the received signal SNR will be decreased accordingly. But this brings another problem. The spatial resolution of DAS is proportional to the pulse width. So increasing the pulse width will deteriorate the spatial resolution. In this work, we proposed chipped pulse modulation to solve this problem. For chipped pulse, the instantaneous frequency varies linearly along the pulse width. And after a matched filter, which is the conjugated and time-reversed chipped pulse, the convoluted results can be greatly compressed. Before compression, the spatial resolution is determined by the pulse width, and after the compression, the spatial resolution can be expressed by this equation, which is mainly determined by the frequency sweeping range of chipped pulse, delta F. So for chipped pore stars, non-pump pores with relatively low peak power can be used to reduce co-propagation penalty, and high spatial resolution can be obtained to increase frequency sweeping range. Next, I will introduce about the experimental setup. This is the DAS system based on chipped pulse modulation. The wavelength of narrow line white laser is 1576.2 nanometer, which is in the L band. A chipped pulse is generated by arbitrary function generator to drive the acousto-optical modulator. The frequency sweeping range is 10 megahertz, corresponding to a spatial resolution of 10 meter. The pulse duration and the repetition rate are 10 microsecond and 1 kHz. Due to the low pulse peak power of about 7 dBm, EDFA and filter is not required. 50 kilometers fiber is used as the sensing fiber. The received signal is acquired by a balanced photodetector and stored by a data acquisition system. The experimental setup is shown in this figure. It can be divided into 3 parts. The first part is a noise loading part. 2 stages of EDFA is used, and the generated noise can be adjusted by the variable optical attenuator at the end. And the WDM channels can also be simulated by this part. The second part is a 96 wavelength real-time 100 GB per second DP-QPSK transmission system. And the third part is the chipped pulse DAS. Because the sensing wavelength is changed to the L band, an OSCAD-L board made by the Fiber Home is used to multiplexing the sensing wavelengths. This OSCAD-L board can combine the C-band, L-band, and the OSC channels, and the measured insertion noise for C-band and L-band are 0.58 dB and 1.4 dB respectively. The use of L-band sensing wavelengths provides an easy solution to add sensing functionality without changing the transmission system. Next, I will introduce about the experimental results. First, the data transmission wavelength is chosen as 1567 nanometers, which is the nearest to the sensing wavelength and the most susceptible to the XPM effect. The solid lines shows that the prefect BR has negligible difference with and without the chipped pulse DAS because of the low pulse peak power. Next, to explore the Raman effect, the data channel wavelength is changed to 1529 nanometers, which is the furthest from the sensing wavelength and has the strongest Raman depletion effect. This dashed line shows that the Raman effect also has little influence. To test the influence on sensing performance, a total of 96 WDM channels are simulated, and 3-meter fiber at an end is wound around a piezoelectric to generate the vibration signal. Intensity variance of the sensing signal along the fiber is used for vibration location. The vibration point can be clearly distinguished with a full width at half maximum of 10 meters. The intensity variance at non-vibration plays as no significant difference with and without the data channels. For the dust system, phase modulation is also performed. To suppress the phase fading noise, the long chopped pulse is divided into several sub-pulses corresponding to different frequency range. And the rotated vector sum method is used to combine the results of sub-pulses. The demodulated phase variation at vibration point is in great agreement with the applied sinusoidal vibration signal. Last is conclusion. In this work, we proposed L-band dust for the first time, and the co-propagation penalty is greatly reduced by the use of a low pulse peak power chopped pulse modulation. And it's also verified that the sensing performance is not degraded with data traffic coexistence in the fiber.